Hi, Professor. We are Group 37, and today we'll be presenting our solution on the Kaggle topic of home credit risk model. So we'll begin with an introduction and dataset overview, followed by EDA and data preprocessing, then model experimentation, and finally our conclusions. So to begin, many individuals have insufficient credit history, making it hard for financial institutions to assess risk. So to address this, alternative data have to be incorporated in the model. And moreover, it is important for the model to be both accurate and stable over time. So ultimately, our objective is to build a model that predicts the probability of default whilst achieving both strong predictive performance and stability over time. Firstly, we observe that our dataset is organized into multiple levels, with depth 0 containing static features for each case IDs, whilst depth 1 and 2 contain historical records with increasing level of detail. Note that a single case ID can have multiple records. Moving on, there are 9 main tables, organized in a relational structure and linked by common case IDs. Each table captures different aspects of the applicant, such as loan applications or demographics. Moving on to the next section, we first look at EDA, which helps us understand the dataset, identify patterns, and detect issues before modeling. So here we focus on 4 areas: target variable, missing values, feature target relationships, and feature correlation. So firstly, we analyze the target variable to understand class distribution. And here we see that our data set is highly imbalanced with only about 3% of defaults. And this actually makes the accuracy misleading, as the model could predict only non-default cases. Hence, solutions include using appropriate metrics like AUC or models such as like GBM and Kaggle. Next, we analyze missing values to assess data quality. And here we see that many features have high missing reads. And if we have to include them, it can introduce noise and reduce model performance. Therefore, we can tackle this by selecting relevant features, adding an unknown category, and using models like GBM that handle missing values effectively. Next, we analyze how individual features relate to the target to identify useful predictors. For instance, when we examine the proportion of accounts with delinquency, we'll see that non-default customers are concentrated at low delinquency levels, whilst default customers show higher delinquency proportions. This could indicate that this feature has strong predictive power. Overall, this step helps us to identify features that clearly separate default and non-default cases. Lastly, analyzing correlations between features help us understand relationships and detect redundancy. From here, we see that the top features already show low correlation with the target, indicating limited individual predictive power. At the same time, similar naming conventions suggest redundancy, which is definitely detrimental as it can reduce model efficiency. Hence, this step is important to help us decide which features to retain or remove. So now moving on to data preprocessing and cleaning. So what we're doing here is to prepare raw data for modeling, ensuring that it's structured and consistent. So what we did here was to first organize the data set into 5 categories, with each category capturing a different aspect of the applicant. This is so that we can handle the data more effectively for preprocessing and feature engineering in later steps. Moving on, we define the base table as the foundation for our modeling process, which means that features from other tables are aggregated and joined onto this base table. So this ensures that each row represents a single loan application with all relevant information. So now to finally kickstart the process, we first handled missing values to reduce noise and improve model performance. We remove columns with excessive missing values or low information, such as those with more than 70% of missing data. Numerical features with missing data was also tackled using like GBM, which handles missing values natively, so no imputation was needed. Unknown categories were also introduced for categorical features to handle missing or unseen values, and this addresses potential distribution shifts between training and test data. Next, we standardized column types to ensure consistency and suitability for modeling. We converted each column based on its meaning, such as casting monetary variables to float types and categorical variables to strings. We also converted date features into days from the decision date to help the model understand recency. So overall, this ensures that the model correctly interprets each feature and improves overall data quality.
Okay, thank you, Daryl. So moving on, we perform feature aggregation to handle the multiple source tables in our dataset. So since many of these tables contain multiple rows per case ID, we needed to convert them into a single row before merging. So firstly, for numerical features, we computed the mean, max, and last values. And for date features, we first converted them into integer days and then applied the same aggregation. For categorical, we use the max and last values to capture historical and the most recent state. And finally, we also added a row count feature to indicate how much historical data exists for each applicant. Next, we perform feature engineering. So from the credit bureau dataset, we created debt ratio, which measures how much credit is used relative to total available credit, while the overdue ratio captures the severity of overdue payments relative to loan size. We also engineered the outstanding ratio to measure how much of the loan remains unpaid, and the installment completion ratio to capture repayment progress. We also engineered features from the person and applied previous datasets. So we created the income to annuity ratio, which measures the applicant's ability to afford repayments. And additionally, we derive an ever DPD indicator to capture whether the applicant has ever missed a payment. So all these engineered features are important because they directly reflect repayment capability as well as borrowers' past behavior, which are all strong predictors of default risk. So overall, all these aims to help reduce noise and allows the model to learn more efficiently. After feature engineering, we perform feature selection using a light GBM model. So we retain only features with importance scores above 1.5 to reduce noise and improve efficiency. And as a result, our final dataset consists 309 features with one row per case ID. Next, we move on to model experimentation. So before submitting on Kaggle, we built a baseline model using only the base table. And we obtained an AUC score of around 0.49. So this low score is expected because the model did not yet include additional tables or any of the engineered features. Next, we then compared three models, which are XGBoost, LightGBM, and CatBoost. So from among the three, XGBoost performed the worst with the lowest AOC score, while LightGBM performed better, likely due to its histogram base and leafwise growth. And lastly, CatBoost achieved the best performance overall, but at a significantly higher computational cost, taking around 1 hour to train. Next, we implemented a step-by-step improvement strategy. So starting from our baseline AUC of 0.49, we progressively added more tables such as person and credit bureau data, which significantly improved our performance to above 0.83. And further improvements were achieved through our feature engineering as discussed, as well as adding additional data sets, which brought our AUC to around 0.84. And finally, by combining light GBM and CatBoost in an ensemble, we achieve our best AUC score of approximately 0.845. Hence, our final model is an ensemble of light GBM and CatBoost. And as discussed earlier, we chose these two models because CatBoost provides higher accuracy, while light GBM offers faster training and better scalability within Kaggle's memory constraints. In terms of performance, the model achieved an AUC of around 0.845 and a stability score of approximately 0.671. So although the stability score is slightly lower than the average Gini score, the positive slope indicates that the model performance is at least not deteriorating over time. Lastly, we'll move into our conclusion. So one key takeaway from this project is that stability is just as important as predictive accuracy in credit risk modeling. And throughout our project, we faced several challenges such as hardware constraints due to the large data set size given to us, which led to frequent out-of-memory issues. And additionally, long training times, especially for CatBoost, which makes it difficult for us to continuously improve our Kaggle score when it takes a very long time to be scored against the competition's internal testing set. So for further improvements, we could explore better handling of missing values through imputation and use chat-based feature selection to improve model stability. With that, we have come to the end of our presentation. Thank you for your attention.